Hello and welcome to this tutorial, and today we're going to be covering amplifier power transformers and typical types of faults. You can see from the video what we're showing today are three power transformers which are commonly used in audio amplifiers, and this may be high-end audiophile type. It may be a power amplifier used for studio use or maybe at a music venue, and then also amplifiers which are commonly used for domestic purposes. But before we get into each type of transformer, we first have to really talk about the subject of noise, because everything begins from the mains power which you connect directly to any of the types of amplifiers. And if you look at your home, you have white goods. So you have fridge freezers, tumble dryers, dishwashers. You also have television receivers, maybe mobile phone chargers. And more commonly, you'll also have broadband routers, which maybe are using your electrical wiring system in your home or business or music studio to transfer data. And you may also have noise which is generated from a whole host or different range of appliances which you then connect. And you have to remember that the power that comes into your home also then is connected on a distribution network as well. So what we have to do is we have to ensure or really minimize the effect of any electrical noise which could enter into the primary of these transformers and then subsequently then get passed through then to the audio signal processing circuits. So what the video shows is something which we call a ferrite ring or an electromagnetic interference filter, and these are very common. And really what it consists of is a ferrite core, or it could be a ferrite ring as we're showing here, and the mains power cable to the amplifier would pass through the ring, and then what you would have is maybe 3 or 4 turns, and then it goes off to the power switch. Very common. Or you may have one which is integral built. If it's a cable which is directly connected to the amplifier, you don't have to plug it and unplug it, and it may look like a bobbin. And what the manufacturer have done there is they've just embedded that or put that into the power transformer as standard. Or you may wish to purchase these from any electronic supplier, and you just clip it onto the power cable, and then any electromagnetic interference which is being passed through those power cables would be absorbed by the EMI filter. And equally so, if any electromagnetic noise is being generated from the transformer, then as it passes out of the amplifier, then again it would then be absorbed as well. The other thing that we're showing is a varistor, and again this could be a component which is relatively new maybe to people who are listening, and you think, well, I wonder where that's sort of used. Well, when we think about these large power amplifiers, on startup or power up, often there can be a high inrush current and potential high voltage. So what the varistor is doing is it's connected directly across the plus and minus, or the positive and negative power input rails, and if there's any transient, what will happen is the varistor will then, in terms of resistable change, and then what it will then do is it will then just eliminate that potential over voltage situation. And you would also find these varistors in switch mode power supplies, very, very common. And just be aware that you had an issue maybe which sort of looked as if you had maybe an issue with a power transformer. You have to check if you have a circuit with varistors in, make sure that that varistor hasn't shorted. Now in terms of mounting, if we take the first one on the left hand side as shown, this is the R-core type, and you have a steel mounting plate, and what you'll have are holes, and these could be precision drilled, and the bolts pass through the underneath of the amplifier and then screw into the base plate, or they may just be bolts which pass through, and then you have these slotted holes so it can be moved, and then you would have a washer, an anti-slip washer, and then a locking nut. And normally during manufacture they'll put a thread seal on there. This may be red in colour, and what that's been used for is the transformer of course will vibrate at frequency, and that's just to prevent that from over time the bolts from unscrewing, but also as well it just makes sure that during transit as well there's no chance of that transformer moving around. You may also see a ground lead or earth connection wire, and they may use that as a common connection point to one of the bolts, and that's not uncommon to see. When you look on the right hand side, we have something which we call an EI or laminated type, and again these are very common, and the mounting arrangement would be the same. So you may have fixing bolts that come into the bottom, or the base plate could be threaded, or you may have what we call a top hat type transformer. This is where it has like an outer cage which goes around, and then it's sort of clamped underneath, but again held in place either with 2 bolts or 4 bolts. With the EI, I'm also showing a smaller power transformer, and these are typically what we call 3 VA rating, so quite small, and it wouldn't be uncommon to find these in startup circuits. So when I think about some of the amplifiers, maybe like Denon for example, on the startup circuits, there's typically a 3 VA type transformer here. It's not an R-core or a toroidal type. It will be what you see here, which is the EI type. Now with the EI type transformer, in this example you can see that there's a copper shield which is going around the center section, then connected to the metal work of the transformer, and we'll describe how these are manufactured in a little while. And what's happening there is that they've put an RF filter or a radio frequency filter just to prevent noise either entering into the transformer, and equally so all transformers generate some level of electromagnetic interference because of their operation, and they're just preventing that from radiating out. It wouldn't be uncommon also maybe to find some form of what we call a ground connection, but they could also refer to it then as a drain wire, and often in electrical wiring audio circuits you can often have this terminology of a drain wire. It just means that it's a common ground wire, and noise then may be just routed down to earth then to cancel it out. With the toroidal transformer, the mounting is different. So we show this here with the toroidal transformer fixing kit, and these are supplied, and really what it is, you have a circular metal disc which attaches to the bottom of the amplifier. You have a bolt that passes through, and then the next thing would be an anti-slip mat, and these come in different sizes depending on the size of the transformer. The bolt passes through the center section of the toroidal, and then you have this centering disc that goes onto the top, and then a bolt, anti-slip nut, and then you have then the locking nut, and again common that you would see some form of thread seal on there. If you're working on amplifiers and you have to remove a toroidal and you get sort of stuck on this thread seal, best thing to do there is don't continue turning, sort of back it off and then rethread it backwards and forwards, and really using the nut then to sort of cut through rather than sort of jamming up the thread by just trying to get it out just in a single rotation. And just a bit of insight for that. For some toroidals, that center section there may not be hollow. They may use a potting compound, and then what they do is they just drill through the potting compound, so it's the same diameter, slightly bigger than the mounting bolt. Or you may find that the potting compound from the top, there is no hole, and what they do is they embed in the bottom the nut, the locking nut, drilling slightly so the bolt passes through, and then it then locks down. And this is quite common like with Marantz amplifiers when you have toroidal, and then on the top of the toroidal transformer you'll see that there's like a foam mat, and then the Marantz sticker is then put on top. In terms of cost, the EI or laminated transformer is the lowest cost transformer, and it is commonly used. The next one is the toroidal type, and most power amplifiers have a toroidal transformer inside of there. And then the R-core is the high end. Now the R-core transformer has become more and more popular, and sometimes it seems that maybe this is a new design, but that's not true. If we think about the Cambridge A3i, the Cambridge A3i used an R-core transformer, so this is not something that's new. The A3i has been around for about 30 years. But what you find now is because of the low noise that the R-core transformer doesn't generate, it's very, very quiet in operation, then you find that the R-core transformers are used in DAC players or high-end types of audio equipment. And again, they can be designed and manufactured for a whole range of power requirements. And then what happens during design is that the transformer designer will interface them with the amplifier manufacturer, and there will be discussions around the types of transformer and also the design of that transformer. Now you can purchase generic off-the-shelf transformers, but commonly what the manufacturer will do is they will talk directly with a transformer company, and they will specify a particular design requirement, and those would be bespoke to that brand or that range. And what they provide then is a complete range in terms of power. All right, so when we talk about transformers, often what you'll see is this term VA, and it stands for volts amps, and the VA rating really is the size rating of the transformer. So if it's 3 VA, that's a relatively small transformer, and maybe on a large power amplifier, it's not uncommon maybe to find something in the order of 600 VA, or even 1000 VA, or maybe 1500 VA. And then what they also do is they will choose the design then, not just based on price, but also on noise, because noise, as we said earlier, is the big issue associated with any kind of audio equipment. So the design of the transformer will be such to provide the lowest noise. And when we talk about noise, this isn't just mechanical noise, we're also talking about electromagnetic noise as well. And then what you will find, many of these power transformers have an inbuilt thermal protection fuse, and if the transformer may be overheated, then that thermal protection fuse could operate, and what would happen then is that it would just go open circuit. It's non-resettable, it doesn't reset once the transformer temperature lowers, and that would then render the transformer open circuit, and then you would have to replace it. But we'll come back to that a little bit later when we sort of get into the typical types of faults that you see. Now, in terms of construction, and we'll go a little bit more detail on the next part of the video, what we're showing here are, first of all, the transformer operation. So what we have is we have what we call a primary winding, and then we then have a secondary winding, and that secondary winding can be a single winding, but more commonly in audio amplifiers it will be multi-tap. So you'll have additional windings depending on what the requirements are for the amplifier. And most power amplifiers you require a split winding. So for example, you require 60 volts. One 60 volt winding is rectified and then smoothed to provide the positive supply for the amplifier, and then the other winding then is then again rectified and then smoothed and to provide the negative, or the negative 60 volt supply. And then you may bring that directly in, and then the circuit is such that the multi-tap transformer, they may tap off, say, the positive of that supply and then the negative, and put that into additional circuits to provide maybe the plus or minus volt supplies for the preamplifier stages or other lower voltage stages in the amp. You find on power amplifiers, the power transformer there commonly would have another winding, and it could provide maybe 26 volts, which after rectification and smoothing could be used then for the fan, for the cooling fan. What I'm also showing as well is the enamel copper wire, and the enamel copper wire is used on all of these transformers, and what it is it's copper wire, but during the process it is coated with an enamel covering, and that enamel covering forms the insulation. And then what you see underneath are what we term as coil bobbins. So these are made of plastic material, and then there are machines which will wind the bobbins. So when we talk about a transformer can be both a step down transformer, very common in a solid state audio amplifier, so that means that the power input is coming in maybe 120 volts or 230 volts, and then the windings are such that the voltage then would be reduced. So it could be a 24 volt, could be 5 volt, 30 volt, whatever is the requirement. But if you think about amplifiers maybe which use thermionic valves, then it would be a step-up transformer, because they typically require voltages maybe 300 volts or higher. So that's why we term them either step-up or step-down. And then the enamel copper wire are used to wrap around these coil bobbins, and you can see that the EI transformer construction uses these steel plates, and the EI just comes from, as you can see there, the types of steel plates which are used. And then on the right hand side you will see here a toroidal core. So these machines are able then to wind the enamel copper wire around the toroidal core, or it wraps it around these coil bobbins directly, or in the case of the R core type transformer, again maybe it's coil bobbins or it's wound directly. Now when we apply power or voltage then to the primary winding, and what we're showing here maybe could be an EI type laminated transformer, what happens then is an electromagnetic field is set up. And what happens with the electromagnetic field is as the AC voltage stroke current comes in, you will get an alternating current flow, which in turn then will induce current flow voltage then into the secondary windings. And what is set up is what we call magnetic flux. And you can see here what magnetic flux is. It's the number of magnetic field lines which pass through a given closed surface. So these laminates are then bolted together, and during manufacture what they also do is that because you would have air gaps in between each one of them, commonly they are soaked in shellac, a varnish, normally in a vacuum type environment then to ensure that there's no sort of gaps. And that shellac then is used to prevent these EI laminates from moving. And when you think the power frequency is 50 Hertz, you'll all have experienced this. You may have nothing connected to the amplifier, and what you can hear is this audible hum. Okay, and what that is the transformer physically vibrating at 50 times per second. And these laminations over time, the shellac varnish starts to break down. And this could be a case where maybe you've had the amplifier maybe 10 or 15 years, and over time you think this is getting more noisy. And what's happened is the shellac varnish has broken down and these plates are vibrating. But you might question, well, why would you make a transformer using these metal plates? Well, the reason for that is something which we call eddy currents, and what you don't want in any kind of transformer is excess generation then, or induced eddy currents. And the problem with eddy currents is twofold. When you look at transformer designs, they are extremely efficient when you look at either stepping up or stepping down voltage. It could be in terms of efficiency of maybe 98 or even 99%. But if the transformer design is not very good, what will happen is that you have these eddy currents which are created, and that reduces the overall efficiency of the transformer. The other thing that it does is it will then generate heat, okay? And that's an issue with any kind of transformer. So the reason why they use the EI type laminates is if you are able then to use these multiple plates, you're able then to reduce the amount of eddy currents which could be potentially generated within the transformer, and that's why it is done. When you think about the toroidal type, then it's a continuous. If you think about the R type, then again it's continuous steel strips. So there are eddy currents, but it's less. It's not the same as what you see with the EI. But remember this point about cost. If you have an entry-level amplifier, commonly you're probably not going to find an R-type transformer that would be in there. It's going to be a low-cost transformer. And you can see the different constructions. With an EI, it's laminated steel. If you think about the toroidal, or maybe the donut that you see here, then that's nickel iron. And then with the R-core, it's high-end silicon steel strips, but it's a continuous. And that's what helps then to reduce that overall effect that we see there. And you may say, well, what do you kind of do if you get the noisy transformer situation? Well, what can you do? All right, and what I want to sort of mention here is that loud buzzing noise that you start to hear will change. And the reason why it changes is if you have nothing connected to the amplifier and it's just ticking over, you may hear the noise and it's relatively low level and you say, okay, I can probably live with that. But as soon as you start to run the amplifier under load, then that means that the transformer then must deliver more power, more current, and then as the load increases on the transformer, you start to hear that the hum increases, and then that tells you, that's probably not going to be something you can live with. If it's in a large music venue, you probably wouldn't hear it because you've got the fans inside the power amplifier. But if you're at home and you've got maybe a listening room it's going to just drive you crazy. And the same also in studio. You know, you don't want to be in a music studio and you got 3 or 4 maybe of these amplifiers in a rack, and then you can hear them, you know, literally buzzing away. And of all the different types of amplifiers which I work on throughout the year, you know, the Samson Servo series, say the 120 series, you know, 160, you know, I have a toroidal replacement for that kind of amplifier. And the reason being is that the amplifier is great, no issue, but over time you get this vibration which occurs from the power frequency of 50 Hertz, and literally the transformer, these EI laminates then become loose. And often you'll see like bolts which pass through there, and you can try and tighten them up with a spanner, or maybe you take the transformer out and put a rubber mat underneath to try and reduce, you know, the vibration between the metal plate and the metal base plate of the amp, and it just doesn't improve it. All right, so all that you can do in that case is either A, replace the transformer, and you may be working on an amplifier today where it's obsolete and you can't, or as I mentioned a moment ago, just have a toroidal alternative and then mount that in there. And as we said, with the toroidal and its design with its donut core, then there's virtually no noise whatsoever, and you can't hear that. Now for the enamel copper wire, if we use an example like domestic wiring, if the transformer is a larger VA rating, then of course the copper wire must be thicker, all right? It must be a larger diameter. So on small amplifiers, you know, it is very, very small. On small transformers, very, very small, because very small amount of current. But big power amplifiers, which require a large transformer, then you'll find then that the actual copper enamel wire is substantial. And that also adds into the fact about the cost. You know, power transformers are not cheap to buy for the high-end amplifiers, and even with some of the audiophile ones, you know, it's a considerable cost. And then the other point is sometimes, and I've never sort of kind of understood this, you know, manufacturers are supposed to provide up to 10 years of replacement parts for any product once it goes out of manufacture. And in the case, say, of Pioneer, and also probably another good example would be some of the Yamaha amplifiers, there's a part number for the replacement transformer, and then when you get a price for it, it's nearly as much of the amplifier. You know, it's just bizarre. You know, why would you have a part available which is as much as the amplifier? Because no one's ever going to buy the part. But that's kind of how it is. So when we come to the sort of diagnosis with regard to what types of faults, you know, you've got to be 100% sure that it is a transformer issue, and that's what you need to replace before you go off purchasing these. Because there's nothing worse than you think, yeah, definitely the transformer. You wait maybe 3 or 4 weeks for it to arrive, and then you put it in, and then guess what? It's exactly the same, and that's a big chunk and expense. And if you're repairing amplifiers for customers, you know, that's probably a difficult conversation that you're going to go have them with the customer. Okay. Now, the next part that I want to sort of provide insight into is when we talk about these multi-tap type transformers. So this example here is the Samson Servo series, and it's a Samson Servo 600, and then this shows then the power input circuit, and this is where the mains is connected, and normally this is through some form of Euro type connector, and then it also shows the power transformer. Now when you have a multi-tap transformer, you may also have transformers which we call dual primary, and what that means is that you have 2 windings on the primary of the transformer, and in the case of say 230 volts, you may have one of the windings which is 115 volts naught, and then the other one then is naught and 115 volts. And you think, well, you know, what's that about? Well, because these amplifiers are sold worldwide, it's very good for a manufacturer to have a common transformer, which they can then, depend on the design, can choose to operate it at maybe 0 to 120 volts AC at 60 hertz, maybe for the Americas, and for Europe and some of the other parts of the world, it could be running at 50 hertz and then 230 volts. So what they do is, if it's a 230 volt input, what they do is they just wire in series the two windings. So the two windings then are just wired in series. So then you connect 0, your neutral, then your 230 volts, and then that becomes a single winding, which then of course provides the necessary then to the secondary windings. Or if you're running maybe the transformer on 115 volts, what then happens is the two windings then are wired in parallel. So effectively the two windings then are in parallel, so that reduces the operational voltage, but what it will do is it will increase the current flow. And then if you look on here, this is very common, the manufacturer will normally tell you what is the protection fuse rating required on the power input depending on the supply voltage. So here what they're showing you is if you're running the amplifier on 230 volts, you need a 5 amp protection fuse, but if you're running it on 115 volts, then it's going to be 10 amp. So you can see here as the voltage got halved, the current then doubled, so the protection fuse needs to be increased. And normally this is a time delay fuse, it's a T-type thermal delay fuse, not a fast blow, because of this inrush current that you see. There's also a component on here as well, again, which maybe you've not seen previously. So they refer to something called an NTC 5 ohms at 10 amps. So what this is, it is a negative temperature coefficient, and we call this a thermistor. So its resistance will change based on temperature change. And so what happens here, because this is quite a substantial transformer, as the power passes through, the current passes through the negative temperature coefficient thermistor, its electrical resistance will change, so it will go higher. So it will then reduce the current flow for a small fraction of time then, which limits the inrush current directly then into the power transformer. The other thing that you need to be careful of as well, and again, depending on the type of amplifier that you're working on, you may have a dual primary type transformer, or you may have a transformer like the one which is shown here for the Samsung Servo 600. So on the primary you have 3 wires. You have the 0, which is the neutral supply, you have 115 volts, and then 230. Now if you open say the top of maybe an A&R Cambridge A60, and you look in there, you look and you think, well, there's 2 protection fuses here. Oh, and I'm looking at that one, it seems to be missing. Well, it's not missing at all. What happens here is you have effectively what we call an auto transformer. So this is where the power is then applied, or voltage is applied, and it can be tapped off at any point on that winding. So in my example there, you will have a fuse holder which is used for the 115 volt protection fuse, and there will be a cover over on the top, but there's no fuse inside. What you find is the 230 volt fuse is fitted with the cover plate. What you don't want to do is remove that cover plate, the protection cover plate, plastic plate, and go put your finger on there, because lo and behold you're going to have 115 volts which is going to be on there. Alright, and then again what you don't want to do is think, well, there's a missing fuse, and go and put that in, because as soon as you do that, then you're effectively connecting then that part of the actual winding then in operation, right? And it's not uncommon, right? On some more domestic audio amplifiers, literally, and power amplifiers, you see at the back there's a slide switch, and now what happens, you slide the switch, and this is what's shown here, and you can select 115 volts or 230 volts. And it's not easy, but sometimes you could catch the slide switch and it inadvertently moves across, and then you've reselected a lower voltage. If you apply 230 volts maybe to a transformer which is rated for 115 volt supply, what will happen is the transformer will heat up, and then you'll hear almost like an audible crackling sound as the transformer gets too hot. The copper wire then with the enamel on will start to overheat and then begin to melt, and then eventually the primary winding then will become shorted, and then the transformer is ruined. You have to replace it. On some of the newer type power amplifiers, and I'm going to use Gemini as an example, and this again isn't unique to Gemini. When you look at these Euro sockets on the back of the power amps, they have a fuse holder, and then when you remove the fuse holder you can rotate it and then you can reinsert it again. But what you have on the fuse holder is you have these two contacts, and that is used then to select if the input voltage to the transformer will be 115 volts or 230 volts. So imagine you had to change the fuse for a particular reason. You can't, or even see, there is no correct orientation, shall we say. There's nothing shown on there. And I've had amplifiers which have been brand new, shipped from factory, come into the workshop under warranty saying it's blowing the mains fuse. And what it is for whatever reason that fuse holder has been removed and it's been rotated, the fuse replaced, put back in, and what's happened is the 115 volt winding has been selected. Alright, so when you are working on power transformers, just be aware of that. And then in a moment we'll sort of step through to common types of faults, and I'm going to talk to you about something which you can build yourself, which will enable you really to work on these types of faults for transformers and quickly identify where the issue is. And as I said a little while ago, you need to be 100% sure before you go off and start placing orders for power transformers. Now, just remaining on the circuit schematic here for the Samson Servo 600, you can see where it says power transformer, where you have the primary windings, but then you have multi-dual secondary windings. The bit that I want to draw your attention to is that when we talk about the VA rating, or the volts amps rating of the transformer, often what we're referring to there is the higher current requirements. So here you can see for the power amplifier, it's rated at 6 amps. And then for the low voltage type suppliers, then it's ranged at 0.5 amps. Okay. Now the transformer manufacturer will design the transformer depending on what the load requirements are. But just to be aware of that, all right? It's not a case where you just have, two windings and then a common or a center point 0. And then that's going to be used for everything. Earlier amplifiers, yes, but more modern amplifiers, they tend to separate them out, and it does make sourcing replacement transformers, probably not the easiest thing, shall we say. All right. So if we just move on now, and then we talk about the common causes of power transformer failures. The first thing that I want to chat about is something which we call a dim ball tester. Okay, and you'll find on the channel a number of years ago I just provided or created one of these backdrop videos, and I called it a light bulb current limiter. Now, for anybody who is considering working on audio amplifiers or maybe any piece of electronic equipment where it draws a amount of current, it's not sort of low current device, I would tell everyone, just go build yourself a dim bulb tester or a light bulb current limiter. Okay, it will save you a fortune, because when you think about when you're working on amplifiers, if maybe I have an issue here with a transformer, instead of me popping a fuse in there, switching the power on, and then it blows the fuse, I can use the bulb current limiter then to indicate to me that excess current is being drawn. And the circuit is just so simple, right? So you can't use a modern day LED type bulb. It is a filament light bulb, and it could be 60 watts, which is more than enough for most of the amplifiers that you work on. And what I've done here is I've just used an inspection lamp. And then what I've done is I've just wired in series that filament bulb. And what happens is, if you have a failure of a transformer, or maybe the circuit within the amplifier draws excess current, as that excess current flows through the filament bulb, it will light, and then that will then limit that current coming in and prevent further damage. And as I said to you, this really is absolutely mandatory in the workshop. You don't want to be going and undertaking any kind of repair work without this simple piece of test equipment. And I would say to everybody, go and make one of these. Very, very easy to do. And I will put the link in this tutorial in the write-up description, so if you want to look how you do this, then it will give you more information. But inexpensive to make, use it every day in the workshop, and as I said, saved a small fortune, and it's a really, really good fault finding aid. Now, On the left hand side, what you can see here is an EI type transformer. So this is one of the laminated transformers, and this has been removed, so it's a real transformer that has failed. And the failure can be in multiple ways. Alright, so I'm going to talk about this one first off, and I mentioned this at the beginning of this tutorial. It is not uncommon for these transformers to have what we call a thermal fuse. Now, if we have maybe say a domestic product, say a lawnmower, or maybe a hairdryer, or even a shredder, those devices will have a thermal fuse, but those thermal fuses will be resettable. So what will happen then is that if the thermal fuse reaches its cutoff temperature, so maybe it's 120 degrees, it will operate, it will go open circuit, it will prevent the current flowing through, but once the device then cools, it will reset. Not in the case of the transformers, it doesn't happen. So this is common where maybe if it's just a amplifier, maybe not with a startup circuit, you put power on and you say, well, it just doesn't power. There's no indication whatsoever. And then you then get into there and you can check through, and then you realize, yeah, there's definitely 230 or 115 volts on the primary of the transformer. Then you check the voltage on the secondaries and there's no voltage at all. So isolate it from the mains power, and then when you put your multimeter then onto resistance, you check it and it's open circuit. And what has happened here is that the transformer at some point in time has gone above the thermal protection limit of that fuse. And these fuses are embedded into the windings of the transformer. Now, I'm aware, and maybe some of you will get into there, and then what you do is if the fuse is not embedded right deep in the transformer, you may say on some of the amplifiers, you get in there and say, hey, I've found the thermal protection fuse here, and sure enough it's open circuit, so what I'm going to do, I'm just going to link it out. Just don't do that, right? And you got to remember, this thermal fuse is there for a reason. All right, so what it's there for is to cut off the current flow through the primary, but it's a protection device, and that protection device means that if that transformer overheated, the last thing you want is an electrical fire. Electricity is a little bit more forgiving, say, than gas, but equally so, don't do that, right? So these thermal fuses, and normally the safety temperature will be written onto the thermal fuse. If you've been able to get to the thermal fuse, then replace it. But often these fuses are embedded right deep within, and there's nothing you can do. The only thing you can do is replace like for like if you can source the transformer, and I'll touch on this in a moment, or you have to create an alternative transformer that you can fit, or you go get an amplifier and use it then as a donor amplifier. Now you of course will ask, well, I hear that the thermal fuse can fail, but why does it fail? And the answer to that is multiple. So the first one is that the amplifier would have an operating range, and typically if it's say a power amplifier where you have a cooling fan, you will have vents on the top of the amplifier which allow then via convection the heat to come out. If you stack the amplifier and maybe you put something over the vent holes, then of course the amplifier then can't dissipate that heat. So over time you can get a buildup of heat within the amplifier, and then that could prematurely cause a failure, so the transformer gets excessively hot. It could also get excessively hot if, for example, the amplifier was used for extensive periods. Maybe it's almost like close to its maximum operating range. So it could be able to cope for short duration, but if it's on maybe for 4 or 5 hours of very, very high volume, transformers working very, very hard, you could maybe find that the transformer overheats and then it then fails. The other common cause of failure is it just fails, right? And you might say, well, what do you mean just fails? Well, anything that is manufactured, and if you think about the enamel wire, you would hope that the enamel coating, when it passes through the dryer, it's even throughout, but sometimes it just isn't. You might have a case where it's thinner and maybe thicker in other areas, and then the net result is that it just fails. Okay, so that's covering the thermal fuse part. The other one is that the windings go short circuit. Okay, And then when the windings go short circuit, you look from the back of the amplifier and maybe there's an external protection fuse, and you'll know, right? So you look and the thermal protection fuse is blackened. Literally, the fuse wire inside has just vaporized. So you know some heavy current has been drawn. Now, when you do the fault finding approach, okay, what you've got to do is you've got to isolate that transformer from the rest of the amp. So when I think about the secondaries, which are then connected to the main amplifier board and running different sections of the amplifier, you've got to disconnect them. And the reason why you've got to disconnect them is, remember, if there's maybe a short circuit rectification diode or a bridge rectifier, or maybe one of the high frequency filter capacitors, as we saw in a previous tutorial, was short circuit, or maybe the large power supply smoothing capacitor, one of those was short circuit, or you had an issue in the circuit of the amplifier which was resulting in the output stage being overdriven, or even if you had output transistors that were short, you could mistake and think, oh, it's the transformer's faulty. All right, so by disconnecting it from any of the boards, you're not powering any section of the amplifier, you just purely got the transformer. That's the first part. The next part is, remember, is there anything else which is then connected across the transformer? Now I'm showing here a transformer with wires and connections. That's not always the case. Some Marantz amplifiers will have solder lugs on the transformer, the wires then come in, and then what you'll find is that there's high frequency filter capacitor connected across one of the windings then down to ground. So just make sure that there's no components that are used for noise elimination, like varistors for example, or these high frequency smoothing capacitors, or maybe you have, on some amplifiers, you have a dedicated filter unit, it's like in a metal canister. Just eliminate all of that. So all that you're going to then measure, okay, is the current drawn by the transformer. And guess what? Just then power it up via your dim bulb tester. You don't have to, check it and wait for it to blow a fuse. Now, if the dim bulb tester lights very, very brightly, you know straight away that there is an issue with that transformer and that the primary winding of the transformer is short circuit. So then you have to replace it. In the video where I'm showing next to the EI type transformer is a great example where the original transformer cannot be sourced. Okay, so this is actually a Pioneer A10 type transformer, and the cost of this is just as much as the amp. But the Pioneer A10, A20, A30 are good amplifiers, so you don't want to throw it away. So what I've had made here is a toroidal replacement, and you look at it and you say, hey, okay, I can see what it's doing. So it has the same VA rating. It has inbuilt into that toroidal there a thermal fuse, so that's good from a fire protection point of view. And then what I've manufactured here are base plates. So these base plates, you have a through hole where it locks the transformer with the anti-skid mat, and then there's two strips which are like sleds, and then the reason for that is I've got to raise it up off the base plate because I've got a mounting bolt that goes through, and that's where that mounting bolt then fixes. And then you have four holes, and they go, or the original four mounting bolts pass through there, and then I put onto there, then locking nuts. Now on the audio amplifier servicing channel, you will find that there is one of the small videos, and what it shows is quite an extensive range of transformers. Okay, and I carry a huge stock of different types of transformers, and then over time what I've done here is I've had these transformers custom made with a particular part number, and then I'm then able to replace some of these transformers which are now obsolete. The other point that I want to mention as well is sometimes you're not able to source, for example, a particular transformer. You can get the VA rating, but you can't match the voltage on the secondary. So let me take an example. Maybe you have a transformer that's failed, and the secondary voltage, for example, and it would be maybe on a label on the side of the transformer, or you have to refer to the service manual or maybe the schematic to determine what the secondary voltages are. But maybe it said it was 31.5 volts, and you're looking around, you're thinking, yeah, I can't source that. So what I can source is maybe a 36-0-36 and that'll be fine, is what you think. Well, it's not fine, and the reason why it's not fine is if you connect that 36-0-36 for a 31-0-31 transformer, you got to remember, first of all, it's going to be rectified, and then here comes the crunch. What will happen is those smoothing capacitors there will have a particular rating, and those capacitors will charge up to a peak value, peak voltage, and it will be substantially higher than what would be the voltage which would be coming from the transformer. So now what has happened is two things. First of all, you have increased the operational or the operational voltage of the smoothing capacitors, and most electronic devices should have a minimum protection of about 20%, right? All of a sudden, that capacitor doesn't have, say, a 20% operating safety limit. You're pushing it, maybe the capacitor is rated at 80 volts. All of a sudden, that capacitor now is being pushed to maybe 78 volts operation. And then the amplifier is running, and then after a short period of time, the capacitor fails. Or it's already overrated, right? So if that's the case and you can't source exactly the voltage that's required, just come down, right? Now, I appreciate, that's not ideal, but if you come down, then you're not going to be in this unsafe area, okay? But when you replace any kind of transformer, remember that you'll need to make the necessary voltage measurements, and in most cases you will need to readjust the bias current then for the output stages as well then. So anything that you do, you've always got to bear in mind from a safety point of view, and always make sure that you work safe then. And then we just mentioned this previously, where you have this buzzing sound. Even with toroidal transformers, you can have a low level buzz. That's quite normal. R-core, not so much, but definitely on the EI type transformers. And you might attempt to sort of dip the transformer maybe in shellac and let it dry. Maybe you can kind of recover it. I've had some success in the past, but over time now, if I can, I will then just look to replace it then with a toroidal type. So really that brings us to a close now for this tutorial. So I really thank you for stopping by and listening. And again, if you've got any sort of comments, any feedback, or you need any further insight or help or information, you can at any time just email through to Audio Amplifier Servicing at AOL.com, and I'll be happy to respond back to you normally the same day. And again, if you've got any sort of requests for future tutorials, I think probably the next one that I'll look at doing is maybe on potentiometers, because again that's something which is often asked about, and I'm more than happy to put together another tutorial and many more as we go through. So I wish you all well, and thank you. Until the next time, bye bye.